Hi, I'm Peter Rowlett.
And I'm Katie Steckles. And Peter, what is today's mathematical object?
Well, do you know when you finish a cup of tea and sometimes there's a little light pattern in the bottom of the cup, a little curvy thing that looks a bit like a heart?
I mean, I can't say I've ever finished a cup of tea. That's not the kind of thing I would do, unfortunately.
Anyway, it's called a cardioid and it comes up in all sorts of places. And we have a very special guest who's come to tell us all about it. So hi, Dominika.
Hi, I'm Dominika, and the object I've brought today is a cardioid. It's a two-dimensional curve that some people say looks like a heart. I think it looks a bit more like a certain part of anatomy, but we can call it a heart.
Like a cleft chin.
A cleft chin, yeah.
Let's go with that, yeah.
Yeah, like my chin, if you view it from above. But yeah, it's kind of, it looks like what would happen if you took a circle and poked it with one finger until you had a bit of a dent in one side of it. That's kind of the best visual description I think I can give.
Yeah, it doesn't look like a heart in the sense that it doesn't have a point at the other end. Like a heart would have a dimple in and a point at the opposite side.
Yeah, a heart on a playing card has a very much, like it has almost two right angles. It has one at the top and one at the bottom.
Yeah.
Yeah.
But yeah, this is more of a... Yeah, it just literally looks like a bubble that someone's poked in from one side.
Mm-hmm. Though what's kind of interesting about that is actually, so, you know, you label different parts of shape so that you can talk about them. And the pushed in bit is called the cusp, which kind of makes sense. But the opposite side of the cardioid to the cusp is called the vertex, despite having no kind of angle at all about it.
Yeah, it's just the edge of a circle on the other side, right?
Yeah.
It's sort of indistinguishable from all the points around it. Just one of them's the vertex. Yeah.
Yeah, there's a fun fact for you today. I mean, it also has a diameter defined, which initially seems a little bit counterintuitive as well, which is the distance from the cusp to the vertex. And this is the thing I had to go and look up because, you know, obviously on a circle, you know what a diameter is, but this thing looks like it's got all kinds of different distances all around.
So yeah, I mean, because if you're at the cusp, as in the pointy in bit, across to the opposite side, depending on which opposite side you choose, there are loads of different lengths. And then as you move away from the cusp, there are loads of different lengths. But I'm slightly fascinated to hear that the cusp to the point opposite is the diameter, because that's not the longest interior length, is it?
Yeah, I've kind of played around with this in terms of when you're talking about shapes of constant width, you say what is the diameter of something that isn't a circle, and you know if you want the diameter of a square, well it's not the distance across the middle because that's shorter than the distance from corner to corner, and you kind of end up with this definition that sort of maximizes the longest internal kind of line that goes from one side to the other. But yeah, I guess if you're imagining a circle that you've kind of poked one side of in, I would have thought the diameter would be the diameter of that original circle before you do the poking. But that, you know, the sort of top to bottom distance, if you're poking in from the right or the left, I guess, the top to bottom distance would be the longest. But then you're kind of pushing it in from one side. And so the diameter is, I guess it's sort of measuring how much you've poked in as well. So it's a sort of useful measure in that sense.
Yeah, but also I think the reason they've defined it that way is that actually if you define a series of chords that all go through the cusp of the cardioid, these all have the same length, and that's the same as the length from the cusp to the vertex. So that's why that particular distance. Maybe there's worth putting a diagram or something in the show notes if we can do that, because this is kind of hard to describe just on a text thing.
Yeah, I mean, I guess the picture for the episode will be a picture of a cardioid, but I'm now trying to imagine that. So the distance from the cusp, which is this sort of inward pointing corner, to the vertex, which is like, if we're imagining poking in from the side horizontally opposite it on the circle. And you're saying the distance from the cusp to any point on the edge of the circle?
No, it's any chord that goes through the cusp.
Ah, okay. So you've got a point on the edge of the circle and a point a line from there that goes through the cusp and hits the other side of the circle.
Yes.
Or the cardioid.
And it has to go. It has to go through the cusp in order to be the same length as this diameter.
Yeah, I'll believe that.
Yeah, that sounds plausible.
If one end of that chord is the cusp, then you're in that sort of trivial case. And then I'm guessing if you move it away from that, say upwards around the cheek of the cardioid, if we're going with that analogy, then it kind of goes through the cusp and off to the other side, and it'll get sort of it'll stay the same length, I guess, because it gets a bit longer on that end and it gets a bit shorter because you're kind of nearer on the other end, maybe. Yeah.
You get the bigger part, kind of, if we're going to angle it upwards, say, compared to that trivial diameter, then that bit tilts upwards, and then you get that tiny bit in the cheek, if that is what we're going to call it.
Yeah.
That should be the new official term for that part of the cardioid.
Yeah, so this is a shape, and I guess we've described the shape in many ways here. So I guess this has like an equation, right? This is some kind of, specified mathematical curve. Yeah,
there's a few different ways to represent it. A lot of people go for polar coordinates because it's got this kind of roundness to it.
So polar coordinates, if you imagine a plane with 2 coordinates for each point, you can get to any point by going along the x-axis and up the y-axis by the relevant amounts. But you can also get to any point by starting with a line of the right length that's sitting on the x-axis and then rotating it until it hits the point. And that's what polar coordinates are doing.
Yeah, so it's kind of every point is specified instead of by a distance across and a distance up, it's specified by an angle and a sort of distance away from the centre.
Yeah, like how far from the origin it is, yeah.
Yeah, and for me, this feels like something that I learned about when I was doing A-level maths and was like, cool, I imagine they're useful somehow. At some point, I may need to know about this. I don't think I've ever used polar coordinates since, although I know sometimes if you look at kind of complex numbers and stuff, they become more relevant again because you can think about complex numbers in terms of the angle and the distance, and trigonometry happens, and it's very fun.
This is where I've used them is complex numbers, and it makes a lot of stuff in complex numbers much easier to handle because, multiplying a complex number moves it further away from the origin and rotates it and things like this. And it's also where the e to the I pi equals -1 comes from. That is a polar coordinates equation.
Yeah, so I can imagine how a cardioid, because that is something that kind of almost draws a loop around the origin. I'm now thinking that it's closer to the origin when you're at the angles near to the horizontal, and then it gets further away as you go around, and then it comes back closer in again when you get back to the cusp.
I think you've made a choice of origin there, right?
I have there, yeah, but it's somewhere in the middle of the cardioid. Sure. But
that seems to be what the general consensus for the point of origin should be, and this, I think, comes about because of one way that you can actually generate this curve using circles in some space. So the cardioid is the shape that you get if you take 2 circles with an equal radius. You've got one that is completely stationary and the other one that is just touching it at one point. Then you take the point where they're touching, roll the circle kind of on the outside around the full length of that inner circle and trace out the curve that you get by that point.
As it happens, I'm just looking at that image on the Wolfram Mathworld site. Like if you imagine you've got 2 pennies touching each other and you draw a red dot on one of them where it's touching the other one, and then you roll the one with the red dot around the outside, and as it rolls around, it's the path taken by the red dot. So it kind of bounces out as the penny spins and then comes back in again and then bounces out and back in again.
Yeah, I'm almost imagining, because like the polar coordinates thing, because your 2 directions are sort of angle and distance, you can almost unwrap it, I guess, and flatten it out into a rectangle. And I'm imagining the cardioid is what happens if you got like the trajectory of a bouncing ball and wrapped it around into a circle. So that really kind of fits with that.
Yeah, pretty much.
Cool.
Yeah, but I introduced that because the polar coordinate definition uses an angle that kind of uses that rolling two circles around analogy. So the equation for this thing in polar coordinates, if the radius of the two circles is a, and the rolling angle, so I think that's where you're starting the point is basically, is phi, then you end up with the equation of the cardioid as 2a, open bracket, 1 minus cos phi, close bracket.
Okay, there's a cos in there. It
Yeah,
sounds
there's
like
cos.
that's going to happen, yeah.
Wikipedia helpfully converts it to Cartesian coordinates, actually. I went to have a look at it because I was curious now. So if you don't want to use polar coordinates and you put in all those usual substitutions for the angle and the radius, you could have the much messier looking open bracket x squared plus y squared, close bracket, all squared, plus 4ax, open bracket, x squared plus y squared, close bracket, minus 4a squared y squared equals 0.
Okay, I mean, that sounds to me familiar, and this is really stupid, but you know how it kind of looks a bit like a heart? I've definitely seen a mathematician Valentine's card that has that equation written on it, because it's kind of like a, it's a romantic shape, I guess, to send someone a picture of a heart, or if we're using the other analogy, it's a nice compliment, I guess. Thinking of you. And if this equation's in there, it's sort of like if you're a mathematician, you'll get that what this means is that I'm sending you a picture of a heart shape, but otherwise it's just this mysterious equation. But that rings a bell, I think, seeing lots of x squared plus y squared squared type terms, yeah.
Yeah, it's interesting to look at that Cartesian form and compare it to like the equation of a circle in Cartesian form as well. There's obviously a lot of similarity there.
I'm thinking about that rather than responding. Yes. I was thinking exactly that x squared plus y squared is 1, or is a radius. That's the circle, isn't it? So it's sort of similar to that. But then I was thinking, how does that work with rolling pennies? And it's if one of the pennies is a point, if the one that's rolling around the outside is shrunk down to just being a single point, then it would just trace out a circle, wouldn't it?
Mm-hmm. Yeah,
that makes sense.
Yeah. And I guess when you say rolling around, what you mean is that you've got a circle that's rotating, but the centre of that circle is following a bigger circle around the outside, sort of thing. So there's all kinds of circles going on in the construction of it.
Definitely.
Yeah, I'm just looking at the animation to make sure. Yeah,
there's definitely a good animation here. Like, as a podcast, we're 2 steps removed from animation. We don't even have visuals, let alone moving visuals. But if everyone's imagining that animation, then I'm sure we'll be all right.
So that's cool. So we sort of know roughly where it comes from, and everyone is absolutely visualizing the same thing, hopefully. But so why do we care about this thing? Like, where does it come up?
Oh, all kinds of places that are sometimes a bit unexpected. I think the first place I ever saw a cardioid was as a child playing with a spirograph toy. Because, of course, you've got, circles rolling around circles. So the kind of shapes you get in a spirograph are cardioids or related in some way, some kind of... I should say the cardioid is part of a group of curves called epicycloids, which are all about things rolling around other things. And spirographs obviously have all these circles. So I think that was the first time I saw it and went, that was not the shape I was expecting to see when I did that. And it got me thinking about it back then. But more recently, well, for some value of recently, when I was still an undergraduate, I was up late doing some problem sheets or whatever with a cup of strong tea next to me that I was slowly making my way through. And I had the lamp in my room pretty close to my desk and my cup. And I looked away from my sheet of, probably some quantum field theory or something like that. And I looked at the cup and noticed an extremely bright cardioid-like shape on the surface of my tea, and that problem sheet didn't get finished that night because I immediately went, hang on, what's that? And why is it in my cup? And can I prove why it's in my cup in this particular shape or form? And I played around a bit with moving the cup around, and, you know, the shape that you see changes ever so slightly with the distance from the light source and the angles and things.
Yeah, I noticed the very careful mathematician phrasing of a cardioid-like shape, which is what a mathematician
Spoilers.
would absolutely say when they were like, it's sort of a bit like, I mean, it could be one, but is it? Because I guess it has a precise definition, but yeah, you're getting something with that same structure.
Yep, and it's it was just immediately like full on nerd snipe because it's so unexpected to see it there. So I, you know, moved all the other stuff off my desk, was like, okay, how can we model this situation? So, you know, I was still doing physics technically. It still count. I was like, okay, let's model the coffee cup as a circle because we don't want to try and do anything in 3D, not at this point of the night.
Yep.
And okay, let's pretend that the light source, my lamp, is infinitely far away because that just makes everything a whole lot easier. So you have a circle, and then you have a light source infinitely far away, which by the rules of optics and making things as easy as possible means that all of the rays come in from that point kind of in parallel.
In
to
parallel,
the cup.
there's nothing between them. I remember my physics teacher at school, I still remember that he said, let's assume this light is coming from somewhere infinitely far away, like, say, and then he named the town our school was in. We were like, that is infinitely far away, is it? But he's like,
News to
from a
me.
physics point of view, yep,
Yeah.
might
Yep.
as well be.
It's a pretty good approximation, to be honest. And this is all going to be really visual, which is not great for podcasts, so maybe more diagrams, but
I believe in us. We can do this.
Okay,
So we've got
if
got parallel lines coming in, let's say from the right-hand side.
Okay, from the right-hand side. If we, ignore the fact for a moment that it would just get blocked by the outside of the circle, we're coming in at a bit of an angle, so it's coming into the cup and hitting one side. Then by, laws of optics, we know that the angle that it comes in with relative to the normal of the plane that it's incident on, the angle coming in will be the angle coming out.
Yeah, and like if it was coming against, like if it's hitting the far side of the cup and that was just a flat wall, they would all just be reflected back in the same direction. If it was at a 45-degree angle, they'd all be reflected straight downwards or upwards. But because it's a circle, you're getting each rays reflected in a slightly different way. So the one right in the middle that hits the very centre of the coffee cup goes straight back. Mm-hmm. But the ones above and below that are going to curve in different ways. The thing that this is reminding me of, actually, and I know Matt Parker's done stuff about this, but parabolas have this very specific property that they reflect parallel lines coming in all to the same point. So you get like a focus, and
I was also thinking satellite dishes, and yeah,
and this is why they use them for things like radio telescopes and satellite dishes. So they all reflect it all into the same point. But I know, because I have seen things, that a circle is not a parabola, and that's a different curve. So I imagine something slightly different is going to happen here.
Well, a circle still kind of has a focal point in that if you had a light source in the middle of your cup, let's say, or whatever, everything would come out, bounce off the walls, and everything would come back in. And if you moved that light source, that would still be true. All of these light rays would still meet at a point. So even in this particular case, when you've got all these parallel light beams coming in, because of, as you said, how the angle of the reflected ray kind of changes as you go from the top of the circle to the middle of the circle, how the angle changes. If you start to kind of draw these light rays out, and this is actually what I did that fateful evening, you start to notice that your pencil lines start to overlap a bit as you do this. The reflected rays all start to overlay onto each other, making this shape that kind of doesn't exist but also does exist at the same time.
So the cardioid is, I guess you're saying it was a bright cardioid. So
Yes.
is that the points where multiple rays of light all get sent through?
Yeah.
I guess.
Yeah, they all kind of overlap there, and that's why you get a bright curve in that
Yeah.
particular location.
That's really cool, because I guess, yeah, if it was just a straight thing reflecting it all back again, you kind of almost wouldn't see anything because the light would just come in and go back out again. But the fact that the light bounces around, I mean, I guess maybe potentially bounces off more than one side, or does it all...
We are not considering that level of complexity.
That's a physics too far. So that maybe the light's not strong enough to last that long somehow, physics. But after the first bounce, I guess the direction that all the light rays go in kind of overlaps. I'm now imagining, I love that there's a thing that I'm imagining for all of these things, but the sort of curve stitching thing, where if you draw straight lines, because light rays are all straight lines, but you can draw straight lines and get a curve in the sort of crossing points where the lines cross.
So I was thinking exactly this, that the string art thing, where you're sort of connecting lines to lines. If you do that for straight lines, you end up with a curve, a parabola or something like that. But if you do it with a circle, if you put points equidistant around a circle and you number them 1 to n, and you connect each one to twice its value. So you connect point 1 to 2, 2 to 4, 3 to 6, and so on, and you keep going around the circle like that. I think that's a cardioid, is it?
Yeah, it is.
And there's like some obvious cases, like the number that's halfway around the circle will just be a line that goes straight across to the other side because you double the number. But then the ones in between that, because you're doubling the number, that's not the same as just going to the other side of the circle. So they're all coming out at different angles.
Yeah. And it just creates that. I don't have a great intuition of why it creates that pattern, but it does. And you double the number modulo n if you've got n points, of course. So you're sort of looping back around. Yeah.
Yeah, it's cool. And like same way with the light, all the strings overlap, and the more they overlap, the darker it is in that particular case. So that's how you get this phantom curve appearing.
Yeah, there's some really fun stuff with that, because I found a website once where you could send it a photograph, and it would send you back a big circular frame with pins all the way around the side, a big long piece of string and a piece of paper with a list of numbers on it. And you start from one of the pins and you just follow the sequence that it gives you. And it's obviously worked out using computers somehow how to arrange the strings so that you get darker patches where the darker patches of the photo were. And I guess it's one of these sort of quite, therapeutic, mindful things that you just sit there counting numbers and dodging between the different strings. But if you do it right, you end up with this beautiful string art that is literally just a photograph of like you or your friends or whatever.
Wow.
And that when I first saw that, my initial thought was, how do you work out that sequence of numbers? That's such a clever, I guess, bit of maths to work all of that stuff out. But it should be possible, right, for most reasonable approximations of a photograph. And there'll be a bit of wiggle room in what actually looks like the thing. But yeah, this is the kind of principle that wherever you've got more lines overlapping close to each other, it will look darker. And in this case, it's light rays that overlap that look brighter. And they happen to lie along the edge of this curve because of the way those lines interact with each other.
Yeah, that's really cool. I didn't know you could. Well, obviously you could, like, hypothetically do that, but the fact that someone's actually gone out of their way to make it a sellable product.
Yeah, I'll try and find a link and we can put it in the show notes if anyone wants to find. This is not a product promotion. I've not been endorsed by them or anything. I just thought it was cool.
Maybe they'll send you a free one. But yeah, so it's all very nice to have drawn a picture that seems to kind of show what you're seeing and kind of make sense in that kind of geometrical setup, but that doesn't prove that what you're looking at is a cardioid. And it was like 3 a.m. at this point, and I was like, I'm too deep into this now. I need to know, is it a cardioid or something else? And so you had to figure out a way to turn this picture into some kind of mathematics that could show it either way. And the way that you can go about this is using a technique called envelopes. So the envelope of a group of curve is defined as some shape that is tangent to that family of curves at every point. And you can kind of picture how this is going to be useful, because if you look at the reflected rays that are forming that cardioid, the overlappingness of it, in a way, is hinting at the fact that tangents are going to be useful here. So all you have to do is find a way to kind of express these ingoing and outgoing rays in a way that lets you call it a family of curves. So you need some kind of, parameter to modify that lets you change from whether you're at the top of the circle with a certain angle of reflection, or in the middle of the circle with a different angle of reflection. And it turns out that you can just do it completely based on this angle, because the angle in's the same as the angle out.
Yeah.
So there's no extra bits involved.
This shouldn't be too difficult, because we know what circles look like. Like circles always seem to be like the sort of base case for a lot of these things. Like I know the stuff about like aerofoils and looking at airflow over things. And a lot of the techniques for understanding the airflow of a particular shape involve finding a way to map that onto a circle. Like using some kind of simple transformation, so that you can use everything we know about how air flows around a circle and then reapply that to whatever shape you've got. So like the circle is, there's an equation, right? We know how to define the angle of the tangent at any point round a circle. And I guess if you're basing that on the height up and down the circle, that's slightly more fiddly, but it's still quite doable.
Mm-hmm. Yeah, you just have to draw a bunch of triangles to convince yourself that the angles that you think are angles that are the same are actually the same.
Yeah.
And then once you have an equation for your family of curves, we want tangents. So it's as simple as just differentiating to find the equation of the tangents, in a way. And this turned out to be not so simple for this particular case. Because it just became a whole mess of things after you differentiated it. So I dealt with it by switching over, doing things in polar coordinates and doing like it all in a matrix representation, just to simplify things a bit. But I think Ben Sparks has a number file video out, and he actually goes through doing it all by hand without trying to look for shortcuts like I did. So that's probably a good reference for anyone that's interested in actually seeing the maths work its way through compared to the way I did it.
Well, I know Ben certainly does a lot of stuff in GeoGebra, so he's very much about finding ways to kind of visualize things that are based on equations.
Yes.
You can give GeoGebra a family of equations and it'll do all of that kind of thing for you. I mean, I do know from chatting to Ben that the main reason that he did that video is because he'd seen you talk about this before. So you kind of inspired him to get into this as a problem. That's the way Ben works often, is he hears someone talk about something and then just spends hours and hours playing with it. And I think that video was the result of that kind of thing. But yeah, I think as a topic, that's the nice sort of natural way to extend it, I guess, is to kind of program it and kind of tweak the variables and see how things change, which I guess is the equivalent of moving the coffee cup around on the table, but within GeoGebra somehow, yeah.
Yeah, I mean, back then I didn't know GeoGebra. If I did, I probably would have gone and used it as the tool instead of manually drawing lines on a piece of paper at 2 a.m. But, I
mean, there's nothing wrong with that, right? That's how we all start, yeah.
Yeah. So, yeah, after all of this mathematical faff, I arrived at the equation of this curve. And I looked at it and I went to Wikipedia and I was like, okay, what's the equation of a cardioid in polar coordinates? And it didn't match. And I was like, what? All this effort and it's not even a cardioid?
It's still a cardioid-like
what is
shape,
it?
though, right? We can
exactly.
hedge it. Yeah.
I was like, okay, but what is this? It looks like a cardioid. So I went digging. I was like, okay, it's clearly got a cusp, like a cardioid, but okay, if it's not a cardioid, it's got to be something else. So what other shapes look like this and have cusps? And turns out it's actually a shape called a nephroid, which is kind of like if you took the cusp part of the cardioid, chopped it in half, so we're throwing away the vertex part and only keeping the bum-shaped half, and then reflect the bum-shaped half back on itself, so you've kind of got two blobs instead of just the one-sided.
So more like a number 8.
More like that's a better description than a double-sided bum. Yeah, that's better.
I mean, I feel like the word nephroid, because neph is like kidneys, right? Like as a medical term, is it meant to be like a kidney shape?
Yes, but again,
it's not. Is it?
It's not really
if that's
a kidney
shape. Then that's a heart. So yeah.
It's like if you had like a baby book, very stylized illustration of those two things. And I was like, okay. And a nephroid is also an epicycloid. So you get it in a very similar way to a cardioid when you have rolling circles happening.
Yeah, is it now a circle that you've poked from both sides at the same time?
Yeah, I guess that's the way to describe it. The nephroid is what you get when, instead of having both circles with the same radius, the inner circle has twice the radius of the outer circle, and you still roll that smaller circle around the larger one.
On the way round, it does 2 full rotations, so the bit with the red spot on the penny from our previous analogy hits the coin twice as it goes round. Yeah, I can see that.
Which is why you have two cusps this time instead of just one.
So when you see that in the coffee cup, are you just seeing half of the nephroid? Is that why it looked like a cardioid?
Yeah, basically the edge of the cup is blocking any of the rays that would have made the other half of the nephroid. But I was experimenting with a mirror, trying to get light rays happening on both sides to see if I could make an entire nephroid appear in the cup. And the answer is no, because angles are hard. But if anyone has managed to do this, I would love to see a picture of it, because I personally have not managed to get a full nephroid, and it feels like you should be able to.
Yeah,
but
you almost want for the purest thing, you want like a cylindrical mirror, like a mirror that's cylindrical but mirrored on the inside, and like some lasers or some parallel lasers coming in from one side that are really visible, and see if you can do that. But yeah.
Well, you almost don't want a laser, because a laser is very, very narrowly collimated light.
True.
And the reason you get this shape is because you've got this broad spread of parallel rays. I guess you could do it with multiple lasers and overlapping them or something like that.
You really want a diffuse light far away. That's basically...
Yep.
Infinitely far away, in fact, as far as the town centre. Yeah.
Yes.
Yeah. But this made me cross, because I wanted a cardioid, and so again I moved the mug around a bit and was like, but okay, if I do this, I can make it look more like a cardioid. And this turned out being taking my mug and moving it closer to the light source, and then like the angles of the butt cheeks kind of changed when you did that. And it turns out you can, if you really want to, get a cardioid in your cup. But the only way to do this is to have a light source on the rim of the cup. Instead of infinitely far away, your point source has to be on the rim. Then the cusp appears directly opposite to that in the cup. and you get a full cardioid. You don't even get a half one because the light source is on the rim. So that's pretty nice. And you can prove it the same way that you prove the other curve is a nephroid by doing this parametrization of...
Instead of kind of parallel lines coming in, you've got a point and the lines are radiating out from that point at all possible angles and then hitting the other sides and bouncing. Yeah, and I guess if anyone, when Peter was talking about the curve stitching thing earlier, if anyone looked at that diagram, we try and put a link to that in the show notes as well. I think that kind of has a sort of point where all the lines meet at one side, which I guess makes sense with that. Yeah, that's your kind of light source over there. Yeah.
But in real life, you're not going to have a light source on the point of your cup unless you put it there. So
just right next to a lamp.
Yeah, though what is kind of interesting is that in practice, your light source is not going to be on the rim or infinitely far away. If you're in like your kitchen or something and you are doing this with the lights on your ceiling, they're not quite far enough away to be infinitely far away by a physicist kind of definition. And so you get something that's in between a cardioid and a nephroid. And there's actually quite a lot of debate about what the shape that is in between these two is with regards to this shape in cups and things. There are people who think it's, and I'm going to horrifically mispronounce this because it's French, a limaçon.
Ah, yes, a limaçon. I've heard of this. I can't remember. Was it a looped limaçon? Was that
Yeah, you can get a cusp bit in the middle that has a loop.
Okay, so then if it's not looped, then that's where the cusp is a single point.
Yeah.
Okay. Yeah.
But this doesn't cover all of the possible geometrical setups, so people aren't happy to consider that a completely solved problem. And you actually end up having to do stuff in 3D because obviously I've been working with a two-dimensional circle this whole time, which is great for simplifying, but it's not so good for holding actual tea or coffee. So the fact that the shape of the mug is 3D also gives you some complications, and what you're actually seeing is the intersection of this three-dimensional big reflective thing with the surface of your tea or coffee. And that's how you get the funny loop instead of just the cusp, because it's a three-dimensional thing intersecting with itself.
Yeah, obviously modelling it as two-dimensional was a brilliant way to start, but in practice we can't just ignore that third dimension. It's still going to be there. Yeah, it sounds a lot like my thesis. I was like, nope, two dimensions, there aren't any more than that. Don't worry about it.
Who needs it? Yeah. It's interesting because this whole class of stuff that's made when light reflects off stuff, they're called caustics from the Greek word for stuff that burns other stuff. Because if you put something in that focal point cusp, you're concentrating all of the light rays there. And these end up cropping up all over the place. Anytime you have any kind of reflections, you're probably seeing a caustic. But my favourite silly example of this is the issue that the engineers had with the walkie-talkie building in London, where they designed this lovely futuristic looking thing, but didn't realise or properly account for the fact that the curvature of one side of the building was going to have a focusing effect on the sun's rays. And I think they melted someone's Jaguar car before they realised.
It's like, hang on, my car's really hot. What's that about? It's just a nice sunny day, but why is my car specifically really, really hot? Yeah. I think it feels like the kind of thing that would end up in Matt Parker's book of maths fails of, is it called Humble Pie? That was ways in which people have made mathematical mistakes. But it's the kind of thing that you really should be thinking about if you're building a big, shiny, reflective thing, right?
Yeah, like, and I looked this up as preparation for this because I had heard the story but didn't know whether they solved it or why they made this mistake. And turns out this architect has done this before. He'd built a building that melted stuff.
Oh, wow.
Then they let them build another building, and they've promised that there would be like some shielding in place to make sure that the building did not melt stuff again. And then at some point in the design process, the shielding got removed, probably by someone that didn't know why it was there.
Yeah.
So the walkie-talkie melted cars.
Excellent. I love that.
They've now put the shielding back on, and apparently it's all fine now.
Good.
But I'm not sure I would want to be the person parked in that focal point.
Yeah, they should just mark it on the floor as like warning. Make it spot here. Wouldn't risk it. Yeah. Fantastic. Cool. Well, thank you so much for chatting to us about this. It's next time someone has a cup of coffee, they will suddenly realise that there is maths there that they hadn't even noticed before. And yeah, so is there anything that you want to tell people about, anywhere people can find you online, or anything you've done that you want to shout about?
I guess the easiest place to find me these days is on Blue Sky. My handle on there is @DragonDodo with an underscore in the middle there. It mimics my Twitter that I still have but don't really use anymore for obvious reasons.
Yeah.
I guess if you're interested in seeing the actual maths that I did to prove to myself that it wasn't a cardioid, I have a chalk dust article about this exact topic that you can have a look at, where I kind of go through it a bit.
Cool.
And you should also watch the Ben's number file video for the lovely GeoGebra demonstrations, because mine are like just Desmos drawn graphs, and I can't compete with a GeoGebra 3D lovely animated thing.
I mean, it's all part of the same thing, isn't it? Yeah, we'll definitely stick links to all of those things in the show notes for the episode. And if you want to find me and Peter on the internet, you can just search for Katie Steckles and Peter Rowlett. We are very findable on various different platforms.
Yeah, we both blog at a website called aperiodical.com, where you can find more episodes of this podcast.
And both Peter and I are members of the Finite Group, which is a collective of maths people with a nice Discord community and regular monthly live streams. If you're interested in that, you can find us at patreon.com/finite group.
And if you have any thoughts or suggestions, want to tell us anything about shapes you've seen in coffee cups, please email object@aperiodical.com. The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.